by just sharing today's agenda and kind of put at ease what these presentations are going to look like. I've been getting emails, and I'm taking full responsibility if I accidentally used a word jigsaw in place of presentation, or the term presentation in terms of jigsaw. But if I use the word jigsaw, and you heard me say jigsaw, that was a total accident, because jigsaw is on my mind from general chemistry. They're working on the atomic theory jigsaw, so maybe it popped out of my mind. But there is nothing formal to submit from your presentations today. It's just sharing of content from one group to another. So instead of me just saying everything and you listen to my mouth, we actually engage in conversations with one another. I try to relay that a little bit with some emails and some announcements. I'd like to begin the class today actually by kind of opening up some Chapter 2 content. Chapter 2, Sections 1 through 3. I'd like to share with you things like, what are functional groups? You've got a great idea because you've been kind of pre-reading and preparing for your presentations. Also, in terms of what are alkanes, alkenes, alkynes, and aromatic compounds, just kind of setting the stage and just sharing some pre-information from Section 1. I'd also like to talk about polarity. Section 2 and 3 of your new chapter talk about polar bonds and polar molecules. Should kind of seem a little familiar, but I'd like to just highlight some things I think are important. And because I'm a little sneaky, I'm also going to integrate best I can some intermolecular attractions talk during the talk of polarity. We need to remember things such as London dispersion forces come in 3 different flavors. We call them dispersion, or perhaps dipole-dipole, or a hydrogen bond. How do these molecules with all of these functional groups interact with one another and affect the physical properties? So I'd like to just sprinkle, if I can, some of the later content as we talk about polarity. I'm going to estimate 20 minutes or so for my pre-lesson. Then I'd like to invite you to get into groups by your like number, your functional group. So if your functional group is in a ketone and an aldehyde, you'll meet with others for the same topic. And we'll just kind of arrange ourselves to have a conversation with each other to prepare what we want to say and who's saying what, and did we have similar notes, and just kind of shore up content with one another. When we're finished kind of preparing, we'll start then our functional group presentations. So when we begin presenting, we'll go right in numerical order, so you'll know when your turn is coming up. If you're not presenting, your job is to just simply be a polite audience member and absorb everything like a sponge, perhaps even write a few things down. I am letting you know that if you follow the Google slide deck, you know, my presentation on your Canvas, I just took these slides out and put them at the very end of the presentation. So there are slides that you can follow as they're presenting a specific functional group, and you can find what I would have presented, and it probably will be very similar. So just an area where you can have some slides to write on if that's your learning style. I'm imagining, and I'm just putting it out there, we may not finish all 11 presentations today, and if that happens, that's okay. You just get pushed to Thursday, so you can plan then beginning class with Thursday and kind of wrapping up some final thoughts. This week is the last opportunity to kind of practice and engage in Chapter 2 content. We have a Chapter 2 set of deadlines for this coming weekend. So those are still on. I do want to make some announcements, kind of off the table related to what's on the screen. Many people have been inquiring about tutoring sessions, especially group tutoring sessions. And I sent, is it an announcement or an email or maybe both, about a Monday, Friday opportunity with Samantha in the Learning Center. That is a drop-in. You don't need to create an actual appointment. And I put those times down there, 1 hour on Monday and a different hour on Friday. Feel free in the Learning Center. It's not what it's called. It's called the ASC, the place where they live over there. Just please feel free to drop by if you can, any or both times. group tutoring. You may also still schedule one-on-one time through the scheduler. That's your learning style. More power to you. I'm just offering group tutoring time. Then, with the help of my lovely teaching assistants, we are offering a Tuesday, Thursday session as well. If your calendar doesn't allow you a Monday, Friday opportunity, please listen for this. Every Tuesday and Thursday, upstairs in my lab, which is room 305. I'm on the third floor. The Gen Chem lab is what I call my lab. I will be in that room from 10 to 11, along with my teaching assistant, Grace, who sits in the room with us. If you've not yet met Grace, she's my teaching assistant for organic as well. Of course, Hannah is doing Gen Chem teaching assistant stuff this term as well. But specifically for organic, you'll have 2 adults in the room to kind of be able to have a group session as well. 10 o'clock, upstairs on the 3rd floor in my lab, which is next to your organic lab. For 1 hour, I'm in there. Grace will be in there. It's a time to collaborate. We'll have practice worksheets available so you can kind of collaborate and problem solve. We'll have solution stations posted to give yourself feedback and have just-in-time support from the 2 of us as we collaborate. Please note that there'll be 2 classes going on at the same time, because I've also invited my general chemistry to kind of meet up here, and I'm going to put my organic chemistry and kind of meet back here, and between me and Grace, we'll be able to handle 2 classrooms going on for review work. I'll invite you in Tuesdays and Thursdays, 10 o'clock to 11 o'clock prior to lecture, or a Monday, Friday with Samantha in the ASC. Did I get everything? So yeah, pencil us in. We have a very first celebration of learning scheduled for next Tuesday. So perhaps this Thursday or Friday or next Monday will work before your or heck, even Tuesday prior to lots of opportunity. If you need some help, please come find us. One more announcement related to content for Chapter 2. This is the first I've announced this, so this is new. I am removing the last part of Chapter 2 from required content, infrared spectroscopy. It's in your reading guide. It's in my presentation on the Google Slides, but I don't have enough time to reach mastery with that. I've removed it from Sapling, and I've removed it from your multiple choice test, and it will not appear on your in-class quiz. Infrared spectroscopy. Oh, you'll learn a lot about it because it's a lab that you'll actually run, so you'll have exposure to IR spec. But I mean, and just kind of a feel for what that is. After we learn all about these lovely functional groups, we see, based on their bonding, where they lie on a IR spectrum, and you're able to identify unknowns based on what their spectrum looks like. I feel it's a great lab objective because you're holding one of the spectrums in your hand after injecting it into the machine, and you go, oh, look what I made. All right, so please know that I'm not cheating you from it. I'm just not taking class time. I'm pushing it to the lab objective. All righty. Hey, turn to your neighbor and say, you look good today. Even if you have to stretch that, right? Friends, any questions I might help with before we engage in the first part of our lesson? Questions, cares, concerns? Yes.
In the Chem book, when I was writing down the formula, it had a city line and
That sounds like something I can come look at. May I answer that one-on-one? Thank you.
How many questions are on the quiz?
25. Which is hard for me to pull just 12 or 13 from each chapter. I'd like to make it 100. Would that be all right? It's 25 questions. You're like, lady, calm down. 25 questions, and it is timed for 50 minutes. So it's just the first half of the class. And then, just for fun, we start Chapter 3 afterwards. I need those minutes for instruction, so please don't leave when you're done. We engage in a lesson next. If you would like to, on Tuesday at 11 o'clock, when I am done with the tutoring session, I am willing to just come straight down to the classroom and begin quizzing if you're worried about minutes. If you like to take your time and linger and kind of stare at the page, and I'm kind of like that. I like to draw the structures. Sometimes people like to build, especially later when we have stereochemistry. I can come down to the room early. After I'm done at 11, I'll grab the quizzes and head down. Feel free to arrive early if you're worried about testing minutes. Alrighty. There is no one in the room before us, I'm told, so that should work fine. Or if you have a class before, just try to come knowing that I'll be here early and just hand you a quiz upon arrival. Alrighty. So, test-taking tools for the quiz. Don't worry about an IR spectrum sheet that you probably printed already because I told you to. You'll use it for lab, but you don't need it for here. You are not allowed, I'm just going to repeat, not allowed a chart of functional groups. That's not a test-taking tool page. Where will that be? In your brain, right? I can see it right here, right? But that is not a crutch. I'm expecting you, and I don't like to use the word memorize, so I'll just say remember all of those functional groups based on recognition of structure. Alrighty. Did I say that? I think flashcards are a really good idea. Flash yourself, flash others all weekend long. Right. So in our chapter 2, we're going to begin setting the stage by considering the major functional groups. We introduce a lot of functional groups, talk about how we recognize them in a hydrocarbon chain, and begin sprinkling an idea of how these functional groups affect the physical and chemical behavior of specific molecules. Why do alcohols have such a higher boiling point than a straight chain carbon? Why do aldehydes place their hydrogen at the end and therefore can have a substrate attack it at their oxygen? And it's really just kind of giving us an idea of the future reaction mechanisms we'll be exposed to. Molecular geometry, intermolecular attractions. Is the oxygen sitting up pretty like a target, or is it buried deep in the molecule and not very well able to be attacked? So the functional groups correlate to the properties of the molecules related to their intermolecular attractions. And as I mentioned, the third bullet, which is a good emphasis at the end of the chapter, we're not tackling in lecture, the IR spectroscopy. Alrighty. So let's begin by talking about hydrocarbons. What are they? I mean, they're the flavor of any organic molecule. They come in varieties such as anes, enes, ines, and an aromatic compound. So in our first section, I'd like to define the term alkane, alkene, alkyne, and how do we recognize if a compound is termed aromatic. We need to recognize the line bond formulas and each of their molecular geometries. Now, in the previous chapter, we practiced line drawing. So if I'm doing like, something where I need a pen, if I draw something like this, what does that mean? It looks like a bunch of squiggles. There's 1 carbon, 2 carbon, 3 carbon. On carbon number 2, I have a ketone, a functional group. This is called a carbonyl. That's kind of the flavor of what that last sentence says. I want to recognize functional groups based on the squiggly structures we call bond formulas. We'll draw the Kekulé structure of benzene, which is an aromatic compound, and show the resonance structure involved there. And what does it mean to be saturated and unsaturated for a compound, a hydrocarbon chain? So the direction of laying the foundation, a lot of introductory words. Hydrocarbons, the heart of organic chemistry, these organic molecules contain carbon chains, just as the word gives us, hydrogen and carbon, a hydrocarbon, that's an organic molecule. So the 2 key elements, of course, in any organic molecule will be carbon with its hydrogen. We also understand there are other elements typically involved, oxygen, sulfurs, nitrogen, even some phosphorus, but those are in the functional group part. So when we talk about a backbone of a carbon chain, the hydrocarbon chain, the backbone of a molecule, we look at the word ANE. Do you see how it's highlighted in red? If I see an ANE, I now know a lot about that hydrocarbon. I now know that there are no double bonds, there are no triple bonds, there are only single bonds in an alkane hydrocarbon. And when I name an alkane, it will end with the ANE ending. So it's the suffix that's telling me a lot about the bonding inside the hydrocarbon. Ane means it's all single bonds. Notice, for instance, here I have 1, 2, 3, 4, 5 carbons. The prefix we're learning to represent the number 5 is penta, like a pentagon, penta. So when I name a 5-carbon straight chain, I call it pentane. Hear the ending? Are there any, I would say, any pi bonds in that compound, any double or triple? And your answer is no. The ANE told me they're all single bonds. The PENT prefix told me how many carbons there were. So, of course, not drawn, but we know they're there. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. The hydrogens we know are there, filling the octet of the carbon. That compound has a formula C5H12. Did I count right? 12? Any alkane will have a general formula C sub n H 2n plus 2, where n represents the number of carbons. The plus 2 is used to remind ourselves that the very last carbon will have 2 more hydrogens to fill its octet. And if you're an interior carbon, you only have 2 H's on it. So you might see this written as CH3 parentheses, CH2 taken 1, 2, 3 times, and then there's the terminal carbon at the end. We practice writing formulas like that in Chapter 1 as well. So CnH2n plus 2 gives me the general formula, double the number of carbons, add 2 more H's to satisfy the end, and you've got the formula. What about this structure? I count 1, 2, 3, 4, 5, 6 carbons, and I see that prefix hex, hexa. That prefix we're learning will stand for 6 carbons. That's the prefix for the number 6. What about the term cyclo? What does that structure look like? A cycle, right? So it's a ringed structure. Take the 2 carbons at the terminal end and connect them. So instead of having 2 H's at the end, let's remove those and make open spots for bonding and just bring the 2 ends together to form a cyclic structure. So what is the formula for cyclohexane? Well, I can count 6 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. When I think about the difference between a straight chain, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, what would the formula for simply hexane look like? Tell your neighbor. What is the formula for hexane? Tell your neighbor. I'm stealing from the murmurs I hear. 14, right? Double the carbons, add 2 for the ends. So now, when you count hexane in a straight chain, the straight chain, this is my formula, CnH2n, add the 2 because I need to finish the terminal carbons. But if I'm making a cyclic structure, I got to take the hydrogens off the end, these guys, and make an open spot to bring them around and connect to each other. So notice the difference between straight chain hexane, and cyclohexane. They have a different number of hydrogens because now the carbons are all bonded and nobody's a terminal carbon. It helps me kind of predict the formula, knowing if it's cyclic or straight chain. I'm using some words I wouldn't mind to check in on. Tell your neighbor what you think the word straight chain and what the word cyclic means. Make them describe it to you so I can eavesdrop. Does that seem like a silly question because it's apparent? And yet I've had students say, lady, that's not straight. That's up and down, up and down, up and down, right? Why are you calling this thing that looks like this a straight chain? Well, I understand that, right? When you build those carbons with a tetrahedral, sp3, they do go up and down, right? 109-degree bond angle. But I'm calling it a straight chain because it's not connected in a cyclic structure. It's as easy as that. But I sometimes say words and kind of see nose wrinkles. Let's make sure we know the structure for the first 10 alkanes. Alrighty, and this is my way of practicing nomenclature. How do we count chemistry style? If I hear the prefix meth, I need to finish that word, right? Meth, what do you think of? Sorry. Methane, A-N-E, methane. How many carbons? Will be just one. The simplest hydrocarbon of all, CH4, natural gas, is methane. We know that it would have sp3, tetrahedral configuration. Two of my H's are drawn in the same plane. They would lie flat on the table. One of them would be behind the carbon, so I like to draw that with a dashed line. And then one would be coming out of the table, out of the paper, out of the plane. So I draw that with a wedge, trying to integrate a little from last chapter. So that's kind of a three-dimensional view of a tetrahedral sp3 carbon. Ethane. Eth is the prefix we give for two carbons, ethane, C2H6. I would take the carbon-carbon and make that the backbone, and of course the 6 hydrogens complete the octet on each of those carbons. That's a straight chain, but that's not what it looks like, is it? I could draw 3Ds, but I get challenged. Propane, C3H, 6 plus 2 is 8. 3 carbons in a row. Add the 2 H's at the end to complete the octet, C3H8. That is an alkane, meaning that it is no double bonds or all singles throughout, and prop means 3. Butane, 4-carbon chain. C4H10, butane. What do we use butane for in life? Lighter fluid, right? Flick your Bic, that's butane. How about propane? Some people heat their homes with propane, or your gas grill, you go fill your propane tank. Pentane, C5H, double that and 2 more is 12. Hexane, hexane, C6H14. Heptane, heptane stands for 7. Octane is 8. Oops, did you see what I did? I wrote O for octane. C8H, double that, 18. Nonane, bless you, and decane. The number of carbons in the carbon chain is given a prefix. The ending is always ANE if all bonds are single. You just learned how to count chemistry style in organic. Just as a reminder, CnH2n plus 2, that plus 2 is needed to kind of end the terminal carbons and fill their octet. Yeah. I would have said the same. Greek or Latin, I have no idea. That's a really good question. I'm one of those that just never question, just like, bring it on, I'll memorize, right? And now you're asking me where it came from. I'll have to defer to Google on that and get back with you. I really don't know. It's a good question. In a second category of hydrocarbon, we're going to change the last name from an ANE to an ENE ending. So I'm introducing alkenes. If I see an ENE ending, we now know there is at least one double bond. If I have a two double bond structure, you'll hear it named as a diene. If there's three double bonds in the structure, it will be a triene, and you'll see some numbers to let you know location. So we're introducing ene, at least one double bond. So for example, between carbon 1, 2, and 3 on this structure of 3 carbons, I see a double bond between carbon 1 and carbon 2. We call that propene. Previously, we would have said propane had it all been single bonds. Now I can see propene because I'm introducing a double bond. By the way, is this structure in any way, shape, or form different than the first structure I showed you? Did I just take that molecule and flip it in space? It's the same exact molecule, isn't it? I'm looking at it from this side, or I'm looking at it from this side, but the numbering will always give priority to the origin of the double bond. So I do not need to tell you the origin of the double bond in propene. I do not need to say one propene because you know there's only one position in 3 carbons. Right? There's only one place to put it, and that's at carbon 1. I only have one choice. Same is true in this structure. I can see ENE, so now I know a double bond. I see a prefix hex, meaning that there's 6 carbons, and I see a prefix cyclo, so I know it's not a straight chain, but the terminal carbons came and grabbed each other to form a bond, a ringed structure. I give priority to the origin of that double bond when naming a compound. So if I saw this particular structure drawn again, but see the double bond in a different location, is it really different? Or have I just kind of twisted the molecule in space a little bit? So again, I would suggest there is no need to tell you the location of the double bond in cyclohexene, because if there's just one double bond, wherever it is, that's going to be called carbon number 1. But it will matter if, I have cough drops. It's like you're good. It will matter if we have something else hanging on it, like something else like a chlorine. I do have to know how to number it so that I get those numbers in the lowest order possible when we practice naming. So how about on a piece of paper I can collect from you today, I'd like you to try to draw 1 butene and 2 butene on your paper for attendance today. What would those 2 structures look like? A 1 butene and a 2 butene. Try to draw them in line bond formula. So not like this, but like this. Line bond, that's not really right, but you get my gist. Where would the double bond be located in structure 1, named 1-butene, and where would you find it in a compound where you see a 2 in front of the name 2-butene? ENE tells me there's a double bond somewhere. But tells you how many carbons there are, and the number gives the position where the origin of the double bond starts. You certainly may if you'd like. She asked, can I put the numbers? Okay. And when ready, please peek at a neighbor. Does your paper match? Feel free to check. Right, so the number tells me the origin of the carbon that starts the double bond. Compare your paper to mine. I had drawn the first structure as 1-butene. The double bond is located between carbon 1 and 2. And remember, you would number them with the origin of the double bond given the top priority is carbon 1. So if you had drawn this structure this way, that is absolutely the same molecule. It's just looking at it from the other side. This is still 1-butene. To make 2-butene, we put the double bond between carbon 2 and carbon 3, between carbon 2 and carbon 3, and you know what? Either way you order them, you come up with the same structure. So there's just one correct answer. So we've practiced a little bit of nomenclature along with the ENE ending.
Does it matter if you put the double bond on like the other side?
Nope. Like this?
Yeah.
That is lovely as well. I don't know if I have a preference. You'll probably see me mix it up. I don't know. Let me know. Let's think about this. Oh, I gave myself a hint. Ignore that. Propene, C3CH, double bond CH2. It's an alkene. So if I say there's a carbon, the 3 hydrogens written directly after that carbon tell me those 3 carbons are attached to the first carbon. That's why a CCH3, those 3 hydrogens are on that carbon. Then a line to attach the second carbon, and I see another H written there, so I know that there is a single hydrogen on that carbon. I see a double bond, which someone called an equal sign from previous lesson, and then another carbon with 2 hydrogens coming off. We call this propene. Between carbon 1 and carbon 2 is a double bond. It didn't matter if I numbered them from left to right. I can flip the molecule and number them right to left. It's the same molecule. It is an alkene because I see it contains ENE in the double bond. What is a constitutional isomer of propene that is not an alkene? That means it can't have a double bond. Propose a structure that is, here I'm going to say it, saturated, that it has just single bonds. Propose an arrangement of 3 carbons that has all single bonds and still has the same formula. By the same formula, we have 3 carbons, and we have 1, 2, 3, 4, 5, 6 hydrogens. Now you can just scrap her. You can even write it on your hand, whatever. What's the clue I gave that probably shouldn't be up there because it's giving the answer away? You see, cyclic is how I say that, like a circle is cyclic. So, because here I'm saying, okay, if it's double bonded in a straight chain, how do I keep the same number of H's but get rid of the double bond? We're going to have to attach all carbons in a cyclic structure. That's all single bonds. And I have 1, 2, 3, 4, 5, 6 hydrogens off of each of the carbons. This molecule is called cyclopropane because it's all single bonds. It's a really tight molecule. It's under strain in that tiny of a ring. It would never really exist, by the way. It's too stressed at that bond angle. I would say even a cyclobutane is too stressed in that ring structure. But by the time you get to a nice cyclopentane, the bond angles are stretched out enough that that's very stable. So we kind of have this ring strain when the molecule gets too small. But that's one proposition, right? A constitutional isomer. See how I got to pull that word out again? Same molecular formula, they're just attached in a different way. A third category of a hydrocarbon has a triple bond in it, and they are called alkynes. So if your compound has a triple bond, YNE, ethyne, pentyne, hexyne, heptyne, somewhere we have a triple bond. The priority of the triple bond gets the lowest number, so number from the left or from the right, but it gets the lowest number possible. By that I mean, if I had numbered, for instance, this structure in the opposite direction, the origin of the triple bond would be at carbon 3 to carbon 4. And if I number it from the opposite direction, I can now have the origin at carbon 2. There is a correct way to number it. You must give it the lowest possible number. So it takes a little figuring out when you're naming. I always just start, well, let's start this way and see where I end, and then compare it to the opposite direction. The correct answer is the lowest number possible to tell me the origin of the triple bond. So when I see 2-pentyne, that tells me between carbon 2 and carbon 3 is a triple bond. If I see 1-pentyne between carbon 1 and carbon 2 is a triple bond. And I know it's triple because of the ending YNE. Tell me about the molecular geometry of an yne molecule. Did you hear it whispered? I did. Did you hear it? There was a little rumbling in the room. When I look at this carbon or this carbon, we see that there are two domains. Both of them are bonded, 0 or unbonded. 220 on your Vesper chart tells you the molecular geometry. It's called linear. And when you build these molecules, you will see a 180-degree straight line in that particular region of the molecule. Notice how flat the molecule is for the first 3 carbons. This molecule is sp hybridized. It's going to have a straight line coming out of it. Even though it's not shown, but there is a hydrogen on this end, it would be coming out as a straight line, creating a very linear part of the structure. So notice that, I mean, this is an awful lot of flat line here. When I draw that molecule, carbon 2 and carbon 3 are sp hybridized. I have to make this side linear and this side linear. This goes back to sp3, so I start that up, down motion. Alrighty. We have to draw them with the correct spatial orientation as well. So what is she saying? ANE, we know that's sp3 hybridized. We know that's tetrahedral. That means when I start drawing structures, we see chains that go up, down to show the 109 tetrahedral angle. When we have an ENE, we know that that means double bond. We know that that means sp2 hybridization. That means that it's trigonal planar. And that particular molecule has 120-degree bond angles, like an equilateral triangle. So when you start to see those molecules, you know that those are sp2 hybridized, 120. Make it higher. And then, of course, yne is sp hybridized. We said that's linear. That's a 180-degree bond angle. Did I put Celsius? That's kind of funny. 120 bond angle is different than a thermometer. And then 180 is a straight line. So you're seeing, like, you're minding your own, all of a sudden you have a straight line. That's your clue that there's triple bonds in there, and you'll probably see them, like, right in the middle. So you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's too many. So you kind of see that flat region of the molecule when it's triple bonded. Alrighty. Let me introduce aromatic compounds as well. This is a very special family, an aromatic compound. You'll actually see entire chapters, but you know what? It's not until the second half of the book. So I'm thinking all of this stuff I'm about to say is part 2. It's in the past chapter 10. But there's a very specific chapters devoted to benzene. Aromatic compounds that contain a special type of ring, and the most common example is a benzene ring. You will know benzene. Benzene, a 6-carbon ring, carbon 1, 2, 3, 4, 5, 6, carbon ring. What do you notice inside the ring in terms of bonding? Yeah, so I see kind of this alternating double single all the way around the ring. And so, I can practice those electron push arrows. I can move this bond here, this bond here, this bond here, because I know that they're delocalized pi bonds, and I can create another resonance structure where the double bonds are now between the other carbons, right? I can delocalize them. And the true answer is they're between all 6 carbons equally distributed, right? A delocalized bond says it's not really a short double and a longer single. It's the same bond length between all 6 carbons because that pi bond is evenly distributed, delocalized, creating something we called resonance from last chapter. If you see a methyl group, do you see how I threw that in there? A methyl group on one of the benzene carbons, we now need to know it's toluene. I have to memorize that. I don't know how you're going to do it. I do flashcards if that's your strategy. Benzene, 6-cyclic, look at the name, study the structure. Next flashcard, toluene. It's not methyl benzene, it's called toluene. Flashcard, here's the structure, know the name. If you see an organic acid group, coo. Hey, who's the carboxylic acid group? We're going to hear your coo group. You'll know that this is truly a C double bond O, OH in terms of its structure, but you'll often see that written as COOH because it's quicker. Sometimes even lazier chemists like me will put CO2H and know that that's coo. If you see an organic acid functional group on a benzene ring, we need to name that as benzoic acid. The acid group, when they're up here, carboxylic acid, they'll tell us that any carboxylic acid has an oic acid ending. Ethanoic, propanoic, butanoic acid. You'll hear that when we get there to their presentation. They're probably quickly adding that on, right? Aromatic compounds are very specialized because they contain resonance by alternating double single throughout their bonding. I might have sprinkled these words, saturated and unsaturated. Let's just take a moment and tell your neighbor what you think those two words mean. Take a moment and read, and then turn to your neighbor and talk. What does saturated and unsaturated mean? Right. Friends, what hydrocarbon family is saturated? What ending did we learn that they would get? Ane. The anes are saturated. If you have pi bonds, either doubles or triples, those hydrogens now do not meet the maximum amount. They're called unsaturated. And I heard people discussing saturated, unsaturated fats. Probably might be the most common way you might have heard this before. It just has to do with if there's double bonds or all single bonds in the molecules. So a compound is saturated if it's all single bonds because it's stuffed with as many hydrogens to fill the carbons as it can. Ooh, this is a good one. On your paper to turn in today, let's practice A little bit of constitutional isomer, that's me pulling last chapter in, drawing it in bond line formulas, pulling last chapter in, and now a little sprinkle of the new content. Propose two ways you can hook together the compound cyclopentene that are not cyclic structures. Let's kind of figure out what I'm asking. We better be able to draw cyclopentene to figure out its molecular formula so that we know what else we could draw with the same number of C's and H's. That'd be a good first step. Let's draw cyclopentene. So the term cyclo, the two carbons at the end are going to form a ringed structure. Pent, how many carbons? 5. And the ene, it's a double bond. So pentene, 5 carbons in a cyclic structure, that looks like a house. That's 5 carbons hooked together in a cyclic structure. All right, excuse me. Somewhere in there is a double bond because you said ene. Does it matter where I put the double bond? Not at all, because I'll just move the molecule either direction and I'll still call that position 1. I'll put mine on the floor. That's one way to draw cyclopentene. Mm-hmm. Yeah, so let's suppose it said cyclopentadiene. That's going to require numbers, isn't it? Because that's got choices of where I can put 2 double bonds. So this is an incomplete name because you have no clue of where I want the bonds to be. I have to put numbers in there. So cyclopenta, and then you'd see something like 1, 2 or 1, 3 placed in 1, 2 diene, 1, 3 diene. And so then I would know, okay, let's call this carbon 1. And I finish numbering my structure. If it's 1, 2 diene, they go like this, which is unstable, or it likes to spread. Oh, that's getting better. That's the same structure, but I might have 1, 3 diene. So there is times where I have to tell you the number. And drawing is my forte. I hate to hide that from you. So now let's figure out how many C's and H's we have. Ready? So penta told me 5 carbons. How many hydrogens are on the structure? 1, 2, 3, 4, 5, 6, 7, 8. That's for an yne. See, for cyclic structures, there are 2 minus hydrogens from the terminal ends because you took the 2 carbons at the ends and you hooked them together. So drawing the structure is helpful, isn't it? Each carbon has to have 4 bonds. So however many bonds it's short from 4, those are hydrogens. So here, at carbon number 1, it already had 1, 2, 3 bonds assigned to it. There's only room for 1 more hydrogen. Here, 1, 2, 3 already involved in the bonding of the cyclic structure. There's room for just 1 more hydrogen. At these carbons that are single bonds, there's room for 2 H's. Okay, so now what we're able to do, just kind of by counting, is seeing that there were 8 hydrogens available. And now, Lisa, you noticed something about the formula, didn't you? Where it's CnH2n minus 2. And that's the formula for an alkyne. I know, right? It's ane, ene, ine. You're going to sound funny for a while. So that information told me what kind of bond is involved. If it's not cyclic, it's got to be straight chain. So I know there's going to be 5 carbons in a row, And what type of bond has to be in there? Is a triple. Somewhere has to be a triple. Alrighty, because that's how I can fill the carbons and create octets and only use 8 hydrogens. So let me kind of get my bearings. I'm just going to draw 5 carbons in a row. 1, 2, 3, 4, 5. I'm just sketching. Where could we put a triple bond? Want to say between 1 and 2? I mean, that looks nice. Between carbon 1 and 2, let's put a triple bond. One, two, three, 4, 5, 6, 7. There's no room here. 8. Between carbon 1 and carbon 2, we placed a triple bond. Carbon 1 has 3 bonds associated. It has room for 1 hydrogen. Carbon 2 already had 4 bonds associated, so no hydrogen. Carbon 3 and 4 had 2 bonds, so I have 2 spots to finish its octet with hydrogen, and the terminal carbon had an H3 at the end. So you wrote CH, CH2, CH2, CH3, kind of just bringing out the molecular formula from that bond line formula. Alrighty. The name of that would be 1-pentyne. Because there's choices of where the triple bond could be, I got to tell you where it is, and that's the purpose of number 1. Between carbon 1 and 2, I put a triple bond. Now look at this. Carbon 1, 2, and 3 all had linear geometry, sp hybridization. Carbon 1 and carbon 2 had a triple bond. Coming out of carbon 2, it's still linear. So I have to draw carbon 3 straight across. Carbon 1, 2, 3, 4. Well, there's 5 there, silly. So carbon 4 and carbon 5 are sp3 hybridized. So we just start that up and down stuff again. That's the structural formula for 1-pentyne. Oh, if you could see your faces from my side. Where can we also place the triple bond to create a constitutional isomer? Where would it be different? Between 2 and 3. Excellent, friends. So 1, 2, 3, 4, 5. Between carbon 2 and 3 is a different structure. This would be called 2-pentyne. 2-pentyne because the origin of the triple bond begins between carbon 2 and goes to carbon 3. When you draw the lined formula, carbon 2 and carbon 3 contain the triple bond. And remember, coming out of either side is also a straight line geometry, isn't it? It's a straight line out of both sides of that triple bond. So there's carbon 1, there's carbon 4. And then finally, carbon 5 will go up or down, doesn't matter, straight line, and then it starts to go up, down, if there are more carbons to draw. That's the structure known as 2-pentyne. Pause for effect. Now turn to your neighbor and say, let me try to get a good process. Turn to your neighbor and just share one new thing you've learned so far from being alive in chemistry land. What's one new thing you've learned so far? Make them share with you.
I did it.